Hello everyone, it is July 4th, 2022, and I have found myself in a position where I have a little bit of time here to try to convey an idea through content of my perception of atmospheric refraction. Atmospheric refraction, as it is demonstrated here on this screen, would actually show a celestial and the light emanating from the celestial hitting different points in the atmosphere and refracting angularly. Now, refraction is angular. It's taught as being angular, it's calculated as being angular, and in no way, shape, or form do I believe it to be the 7/6R formulas that populate different calculation programs. And my take on the reason why they utilize the 7/6R is that it is an estimation based on their observations plugged into a radius so that they can write their programs. It's a shortcut. That shortcut, they need to do this because all of these individual angular refractions, they couldn't write a program in order to make that work within their program. And additionally, if they attempted to, it would be impossible for them to slightly adjust their radius in order to make their program fit and show the observations that are actually being recorded. They're able to adjust that radius slightly in order to try to bring their program in line with real-world observations. So this is obviously atmospheric refraction over a globe, and this is the last time I really want to bring up a globe, as I do not believe in the globe model. During my research, which is really focused on refraction and what it is, just so I could really rule out what it is not, I've come across some interesting presentations. This screenshot from a presentation by the University of Rochester caught my eye for a particular reason. The presenter was talking about the path of the laser that they had culminated. It's a red, green, blue laser. They culminated the beam into a single source or single stream, and they shined it horizontally into this gradient index optic. Now, gradient index optic is hundreds, if not thousands, of refractive surfaces inside an acrylic block. And where this may actually appear to be a curve, it's not a curve. It's just the resolution of all of those individual angular refractions are leading you to believe that there is a curved trajectory. And yeah, visually you could say that it is a curve, but in a sense refraction is angular, and there's just thousands of angular bends that are making this trajectory. Now, my thought in this, and again, this is a highly exaggerated refractive environment, that the light, or what would be the sun's energy, at great distance from us on a flat plane, would start to shine more horizontally towards us, or towards the atmosphere above us. And what we're seeing in this particular slide is a hotspot. And to me, that hot spot pretty much represents what we see as far as a ball of energy in the sky. And I would then state that as we move further along this path, as far as distance, if the observer was farther and farther along, that ball of energy would manifest itself somewhere along this trajectory, eventually hitting this horizontal line, which I'm representing as sea or ground level. When this trajectory crosses this line, I would suggest that that is what we recognize as the moment of sunset. And as the sun moves further away, or that this whole trajectory is moving away from the observer, that manifestation of the sun would happen in front of the observer, or what would appear to be below sea or ground level. You would be at nighttime. Now, there's some other things to point out about what we're seeing here. The separation of light into different colors, which the highest band is red. And at sunrise or sunset, the first thing we view, or the last thing we view, depending on if it's rise or set, is red hues. That would be that split portion of the light, because refraction does tend to separate energy into different wavelengths, and the red wavelength is the least likely, or the one that refracts the less. So it is not bent down sooner into the field. It presents itself at sunrise as the first rays, and at sunset as the last rays. Now I'm going to take us to this next slide. And this is just something I modeled up quickly in CAD, which would represent a sun above an atmosphere. This would be the top layer of the atmosphere. And that horizontal projection of light would reach its extremes. Now, at the extremes, light would bounce off of the atmosphere based on total internal reflection. If I'm understanding Fresnel's equations correctly, there is at a minimum angle to a boundary interface, energy will bounce off and not engage that interface. It will reflect off of it. And if it doesn't reflect off of it and it starts entering into the first interface, or the series of interface, which is called the gradient, or the atmospheric gradient would be from zero pressure down to sea level. So the sun right now is at midday, or centered on this field. The extreme points, one would represent sunrise, the other would represent sunset. The total length point to point would be the maximum illumination of the sun. Down below, I've got it tilted on an angle, so you would see, the sun is illuminating a circular area. There's other things that I think come into play with this, which I can explain more as far as light coverage over a flat earth model, but we can get to that later. Everything within point to point, the sun is engaging at a steeper angle, and this would be day. Anything outside of these 2 points would be nighttime. This next image is, another slide I put together for us to understand refraction, atmospheric refraction from this model, and to tie it all together. Again, that original view I put in place, which would show a path through a index gradient ending in a sunset. Now, all three of these bars are the same model. The box image becomes smaller and smaller because I want to really focus on this top section here. I created this model, or this gradient, based on a couple of things. In speculating on how high our atmosphere is above us, I really just lent on the concept of high altitude balloons, and if there's enough air for a balloon to be supported in, which is about 32 miles from my research. So I gave this model 32 units of height. The second number of 6,544 was based on the longest day at the equator when the sun is directly overhead. When the sun's directly over the equator, what most people agree on is the fact that the relationship between the sun and a spot on the equator is about 1,000 miles per hour. And if the longest day on the equator, or when the sun is directly over equator, the day's length is approximately, I think it's just under 13 hours. So half of 13 hours would be about 6.5. Multiply that by 1,000. That's why you have 6,544 units. This would represent the sun being at midday, or half a day, and the termination point where the sun would set. So what I'm suggesting in here is a refractive event. When the sun is over in this area, it is going to hit a point where somewhere along the surface it is going to stop engaging the gradient, and it's going to reflect off of. But just before that, it is going to create a trajectory very similar to a curve, but it's going to start stepping down through this gradient. Again, you have zero air pressure, you have sea level air pressure, or wherever you're at. And that sun will start making a downward path to the point where, like I said earlier, it would no longer reach the viewer because it has appeared to set. But it's only appearing to set due to refraction, atmospheric refraction, and the sun's inability to reach us or manifest to where it creates that glowing spot that we're seeing at the start or the end of this gradient index block. This would also potentially go a long ways in explaining why we have observations of the sun appearing to manifest or present itself to us as being between cloud layers, with distant clouds being behind the sun and clouds being in front of it. Again, a lot of this comes down to understanding refraction. I would suggest that everybody go back to the board on refraction and look at the first equation. How is refraction calculated? What is it? Refraction is the angular bending of light. Okay, it needs to have a interphase, which, and this would be the gradient, the stacked layers from no pressure down to the pressure at ground level. It needs to engage the surface layers at an angle perpendicular to the norm, which is straight up and down, and it will start refracting downward. I can't see where there's anything about this concept that isn't plausible based on the teachings of refraction and what we know and what we observe. But I would welcome responses in the community to see if this is something that's viable. I've already shared with a couple of individuals, and they are encouraging me to refine my presentations here. They're going to be helping me out in the future, and we hope to bring a lot of good work to the community. So thanks for taking the time to listen. Would love to hear what you all have to say. Thank you very much. Bye.